Okay, so in the last video, we were trying to find a way to approximate the function f of x equals e to the x. And we said that one way to do it is by kind of generating a polynomial, power by power, degree by degree, term by term, whatever you want to call it, and trying to make that polynomial approximate the function better and better. There's a formal theorem that makes all of that work, but like I said last time, we're going to kind of combine this into two separate days to kind of really dig into the math, because I want to make sure you understand it because it's important. So for right now, we're going to forego the formal statement of the theorem and just kind of give a formal definition of the polynomials we were working with, make sure we understand how to generate them, and then in the next video, which I'll post tomorrow, we'll kind of mess around with the actual theorem and see what it tells us and what's important about it. Okay, so the actual statement, for right now, don't worry about any of this. For a Taylor polynomial, Brooke Taylor, the guy who came up with this, a Taylor polynomial, I'm calling it p sub n of x. I think your book might use a different letter, but it doesn't matter. P sub n of x, the nth Taylor polynomial for a function, is f to the n, that's the derivative, of a, where a is your center, times x minus a to the n, all over n factorial. So as an example, this is kind of it written out long form. They get kind of big and cumbersome really quickly. It's f of a, the 0th derivative is just the function. Don't worry about it. Evaluated at the center. This would be raised to the 0, so that goes away. And then this would be 0 factorial, which is 1. So it's f of a plus f prime of a, the derivative at the center, times x minus a to the first over 1 factorial, plus the second derivative at the center, x minus a squared over 2 factorial, third derivative at the center, x minus a cubed over 3 factorial, and my board runs out of room, but it keeps on going, out to whatever n that you happen to want. So we did e to the x in the last video. If we did that here, the way we would say that is we want to find the Taylor polynomial where n is equal to, we'll just say 3 because that's what we did before, of f of x equals e to the x, where a is equal to 0, our center. Then according to this, we get f of 0 plus f prime of 0 times x minus 0, which is just x, over 1 factorial, which is 1, plus f double prime of 0 times x minus 0, which is just x squared, over 2 factorial 2, plus f triple prime of 0 times x cubed, over 3 factorial, which is 6. Now I just plug in the function value, but my function is e to the x. At 0, the derivatives are all e to the x, so it's always just e to the 0, which is 1, and I get 1, plus 1 times x, which is x, plus 1 times x squared over 2, which is x squared over 2, plus 1 times x cubed over 6, which is x cubed over 6. And this is actually the polynomial that we generated in the last video. I am aware that this can be somewhat cumbersome to see. Like I said, this is the general form right here. You can put a summation sign in there from 1 to n if you want for the polynomial instead. But you need to be able to generate these. It's kind of a standard skill and trick that you get out of Calc 2. So as an example, and more terminology, these are called Taylor polynomials, but there's also a special case called Maclaurin polynomials. Maclaurin polynomials have the exact same formula. The only difference is for Maclaurin polynomials, the center is always 0. As far as it goes in the way you'll see these problems, you'll either be told, find the third degree Taylor polynomial for f of x equals sine x, centered at a equals pi. Or you'll be told, find the Maclaurin polynomial for sine of x, and then you're generally not told the center because the assumption is if it's a Maclaurin polynomial, the center is 0. But be aware, this is a skill you need to have. It's kind of one of the fundamental things you get out of Calc 2. So we're going to do that right now. We'll use sine of x. F of x equals sine x. We will do the 6th degree Maclaurin polynomial. And now I mentioned in the last video, and it's obvious just looking from this, all the writing for these can be somewhat cumbersome, and I am limited somewhat for space. But as far as how you go about doing this, well, let's see. If I'm going to get the 6th degree to Maclaurin polynomial, I know my center. I'm going to need all the derivatives out to the 6th derivative. So list them all out. So we will have f of x equals sine x, f prime of x equals cos x, f double prime of x, derivative of cosine is negative sine x, third derivative is negative cosine, fourth derivative, I'm already running out of room going down, is sine of x, the fifth derivative is back to cosine x, and I'm just going to have enough room. The 6th derivative is negative sine x. Now I have all my derivatives, but I'm going to need the derivative evaluated at the center, which for us is 0. So now I just need all of these evaluated at 0. And if you have lots of space in writing, you can list out another column here. Here, because these are easy, I'm just going to kind of write them out. At 0, sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Negative cosine of 0 is negative 1. Sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is 0. Now I have all my values of the function at the point. Now I can generate the polynomial. So I do f of 0 plus f prime of 0 times x minus 0, which is just x, over 1 plus f double prime, and actually we're going to shortcut this, all the way out to the 6th derivative at 0, x to the 6 over 6 factorial. Because now I can just plug in the values right there. So let's see. I get f of 0, which is 0, so I don't even need to bother writing it, plus f prime of 0, which is 1, times x, which is x, over 1, plus the 2nd derivative is going to give me 0, so that term will drop out. The 3rd derivative will give me a negative 1 times x cubed over 3 factorial. I guess I can drop the 1 there. The 4th derivative will give me 0 again, so it'll fall out. The 5th derivative will give me 1 times x to the 5th, all over 5 factorial. I dropped my marker cap. Okay, good. And now right there, I get my Taylor polynomial. And maybe you've spent a lot of time doing trig throughout all of your different algebra trig. Calc 1, now Calc 2, we've done a lot with trig. And the question should be, does that make sense? Is that a logical approximation for the sine function? We know what sines look like. They go like that back and forth. So polynomials approximate them well. The only problem is eventually polynomials will shoot off like this or that or whatever, whereas the sine function will keep oscillating. But does that one at least approximate it well? Well, as far as polynomials go, if you remember all the properties of polynomials, that's raised to the 1st, that's raised to the 3rd, that's raised to the 5th. That's an odd function, an odd polynomial. The sine function, if you remember whenever you define sine function in trig, the sine function is an odd function. So it actually seems like it should work well as an approximation. But one more And again, these take a long time. We're going to do the Maclaurin polynomial for cosine. And I would suggest this is a skill that you need to have because it is fundamental to Calc 2 and what we're going to do. On your exam, you will be told, here's a function, hey, sine of x, cos of x, tan of x, e to the x, you name it. Here's a polynomial, here's a function, find the 6th degree Maclaurin polynomial, find the 5th degree Taylor polynomial at pi, find the 3rd degree Taylor polynomial at 7, who knows. You do need to be able to write this all out. But we could find all the derivatives of cosine, we'll use cosine now, and we could do all of that out. Then we could plug in 0. We understand that a lot of the terms will end up being 0 and going away. But now I'm actually going to use a trick. If this is the polynomial that approximates sine, we know the derivative of sine is cosine. So what I'm actually going to do is take the derivative of this one. Because if this approximates sine, and now I want to approximate cosine, and cosine is the derivative of sine, then the derivative of this should approximate the derivative of cosine. If I do that, derivative of x is 1 minus the derivative here. Bring down the 3. It'll cancel the 3 in 3 factorial, and you'll be left with 2 factorial with an x squared on top. Plus, here, bring down the 5. It'll cancel the 5 and the 5 factorial. You'll be left with 4 factorial and an x to the 4th on top. And now I'm not actually writing this. I wanted the 6th degree polynomial, but assuming this is correct, the next term is pretty obvious. Minus plus minus 2, 4. The next one should be 6. 2 factorial, 4 factorial. That should be 6 factorial. I would suggest doing all the work out. I didn't do it here to save time. Doing all the work out and seeing that that's correct. But again, if you think about it, this is clearly degree 0, 2, 4, 6. It's clearly an even polynomial, an even function. The cosine function is an even function. So it makes sense that this one should be able to approximate the cosine, just like this one, the odd one, approximates the sine. And one thing I would point out, and the thing to really ponder to kind of see what's going on here, these are approximations. How can I make my approximation better? Well, I could pick the next value. Maybe instead of doing this, we can see the pattern here. Clearly the next value should be a minus because they alternate. X to the 7th over 7 factorial. Well, that approximation's better. How do I make it even better? X to the 9th over 9 factorial. And so on and so forth. And the fundamental math trick, thanks to Taylor, which we'll see in the next video, is that these polynomials approximate the value of the function. If I just turn it into a series that goes off forever, the series will actually be the function. We saw that a little bit with the exponential function. We took its derivative and saw that it was the same series. Same idea here. If this is sine, if this series, if it goes off forever represents sine, I take its derivative, I get that, which means that's the series for cosine. If that's a little bit bizarre, like I said, that's the theorem that we're going for, and you can kind of ponder that and think about that between now and when I do the next video for tomorrow. The main point here is you need to be able to generate these polynomials and understand. I only did Maclaurin's here, but you also need to do Taylor's. The only thing that would change is where your center is. And then ultimately, once we can get the polynomials, then we can start manipulating them. Take this polynomial, take its derivative, get a series, take its derivative, maybe manipulate the series some way, change my x's around. There's a lot of interesting algebra you can do once you get a grasp on what's going on here. And that's what we're going to kind of go into next.